Okay, thanks everyone. Thank you so much for joining us for our next GoAERO expert lecture. I'm going to introduce GoAERO CEO Gwen Leiter.
Hello, everyone. Thank you for joining us today. We have once again a phenomenal expert lecture. As you all know, these expert lectures, as well as the GoAERO Prize, are brought to you by GoAERO and our phenomenal partners, including Boeing and NASA and RTX and Honeywell, and over 30 different aerospace and first responder organizations around the world. We are so very pleased today to welcome Dr. Dominic Barone. Dom is the manager of Future Flight Concepts of the Future Flight Concepts program within Boeing's Sustainability and Future Mobility team. He's responsible for leading an enterprise-wide team to develop alternative energy solutions to achieve aviation net zero goals in 2050. The team is responsible for creating and analyzing new aircraft concepts, identifying new key technologies, and transitioning those technologies to product design. Prior to his role, Dom worked for Boeing's subsidiary, Aurora Flight Sciences, as the manager of the Electrical Propulsion and Power group. We are so very lucky to be able to have Dom share his expertise with us. And thank you, Dominic, for joining us today, and take it away.
Great. Thanks for having me. I'm excited to be here. So I'm happy to be here. Great to get a chance to talk to everybody, and I'm going to talk a little bit about some of my experience in propulsion selection, and hopefully convey a lot of the things to be thinking about when designing a new vehicle, and all of the key pieces. As Gwen so nicely said, I'm here in Boeing in Sustainability and Future Mobility, where a big part of what we're working on is how do we get to net zero? And a big piece of that is propulsion selection. So I'm going to use that as sort of a base on which to build a lot of the discussion on. I know it's slightly different than what GoAERO's things are, but all of the same processes and thought processes go together to make that thing. So quickly, I'll go through my presentation. I'll give a little bit about my background, a lot of conceptual propulsion system design and product design, so you can kind of get where we're going, and then a lot of the key aspects, understanding requirements, energy carriers, especially how we're changing fuels and what new fuels can be like, powertrain, safety certification, and kind of wrap it up. So my background is pretty varied. I have my bachelor's and master's from the University of Cincinnati, aerospace engineering. I got my Ph.D. at the University of Virginia. Got to work on a lot of great projects during that. I started working on scramjets in my undergrad and master's days, doing combustion testing, lab support, data analysis, and then ended up doing my master's in later diagnostics, and trying to understand exhaust and properties within scramjets. So worked pretty much directly on X-51 at the time. Then at University of Virginia, where I got into my brand new design of a propulsion system for submarines, which was actually an aluminum water reactor for propulsion. So doing a completely different thing, going from the upper atmosphere, high speed, to underwater stuff, new problems. And then what I actually did my dissertation on, which was some multi-phase fluid dynamics on the inlet for turboshaft engines for helicopters and things like the V-22 to prevent dust ingestion. I then started my commercial career at GE Aviation, where I was able to take something, the LEAP 1A, from first engine to test through certification as a performance and testing engineer. So got to actually work on real certification, getting all the real testing done to get that engine on an airplane. And then I got back into the conceptual world with hybrid electric systems, the design and development of a 1 megawatt electric powertrain. Then I moved from the engine company to the airframers at Aurora. where I put together some options for autonomous vehicles and understanding propulsion and integration there, as well as electric aircraft propulsion with EPFD, which is a program with GE, my old team at GE, my new team at Aurora. We put together a program there, and also worked on so a lot of the conceptual propulsion system design for X-65 and X-66 in my time there. And for the last 2.5 years, I've been here now in Boeing proper, in sustainability and future mobility, where we look at pretty much all of the different propulsion systems. So as I'm going through this, I have a wide background in different ideas, different crazy ideas, and how to get them onto airplanes. So that's what's coloring a lot of this. And where do we start when designing a new propulsion system? It's always with requirements. So it's really important to take some time and understand what it is you're trying to do. The very first thing, I put this here in a couple of 4 main bullets, and this can be, sometimes even years of effort to understand what these are. What is it that you need your aircraft to do? What is the mission? So understanding how the aircraft is going to operate, what's going to happen. Certainly from my perspective, the engine and propulsion system is pretty much the #1 thing that will drive how the aircraft operates. For instance, if you're going to go long range, you're going to have a classical airplane with wings that's going to keep the airplane up in the air. If you need to go short missions and you need things like vertical takeoff and landing, you start looking at helicopters or now distributed eVTOL propulsion. Certain different configuration aspects really will determine what you can do based on what that mission is. So, how far do you need to go? It's going to drive a lot of different things, and it's going to drive, what kind of fuel you need. Can you use a battery? Can you use something else? Do you need to go to jet fuel type of things? Where does it need to fly? That's actually, a question people always don't always think about. What support resources are going to be available where you need to take off and land. Today, traditional airplanes all fly in and out of airports. Pretty much all airports have jet fuel available. Most, if not all, airports have avgas available. So if you're flying a small general aviation airplane, you could pretty much, or a large commercial, you can pretty much go to any airport in the world. Although sometimes they're not quite there. But if I want to fly electrically, will I have charging resources available? If I want to create a hydrogen airplane, will I have hydrogen available at that airport? And what are those infrastructure things that need to change to get the airplane in? Do I have the maintenance pieces available? Do I have an ability, if something goes wrong, to fix it? Those are a lot of the key things that we always have to think about very early on in the design of the aircraft, and understanding how that's going to impact the choices of all of our systems, particularly propulsion, as well as all the other systems. And then, of course, the big ones is, what does your customer actually care about? What are the high things? Certainly in commercial aviation, cost tends to be one of the highest drivers. Speed is important. Emissions is now what I'm worried about quite a bit. And then availability. How useful is your airplane? How often does it have to go down for repairs or maintenance? And you're going to trade a lot of these things. Certainly if you're looking at a military aircraft, your cost might go up, and to be able to improve speed or availability, they may not care about emissions so much. In commercial, it's interesting with speed and availability and cost. You might sacrifice some aircraft efficiency to fly faster. For instance, we all know any aircraft that flies slower is actually probably going to be more efficient overall, but it might not be overall efficient in a fleet network. You need that speed to get people somewhere faster, so that airplane is now available for its next flight sooner, and so you can move more people faster. So overall, as a system, it can be more efficient, and that's really where we get to, particularly in sustainability, and thinking about aviation is always a system of systems problem. And I want to walk everybody kind of through this chart a little bit because this is how we're thinking about it today and how we do our assessments of different propulsion systems for the sustainability problem. So traditionally, we've thought of an aircraft, as a fuel burn number. What's the SFC, or the specific fuel consumption of an engine, is kind of big driver, or what's the block fuel burn per, you can look at available ton kilometer, or some other metric of how far and how much fuel did I use to use something. But that really just focuses on what we call the tank to wake. So, looking at the engine in the airplane, I put fuel in the tank and exhaust goes out the wake, and there's some efficiency there. When we start considering our energy carrier in this case, so we're talking about how does our fossil Jet A compare to our SAFs, or our drop-in replacements? What if we want to go to hydrogen? What if we want to go to battery electric? What do we have to consider to do that? Because, in short order, jet fuel is like the best fuel for an airplane. We've refined it and gotten it to be pretty much perfect for how we operate airplanes. It stays liquid everywhere we need it to be liquid. It packages well. We basically get our fuel tanks for free and the wing. It's really a great fuel. That's why SAF and being able to sustainably produce jet fuel is such a great option for us, and where we're putting a lot of our efforts. But there's other things to think about too, which is how much is it going to cost us in terms of available resources to make that SAF? We'll have bio feedstock available. We'll have carbon capture available, green electricity available. If I use those same resources, does it make more sense for us to do something like hydrogen or battery electric? And that's where our well to tank piece comes into this, and we can look at the whole thing as well to wake. So as you're thinking about your aircraft and your propulsion system, you're kind of thinking out, we're certainly thinking right now in this entire space of energy usage from beginning to end, to make sure we are coming up with some of the best solutions for the future and overall emissions. And so kind of keeping how that goes through, obviously we can use combustion engines. They'll pretty much work well for any type of fuel, except batteries. But batteries, you can drive fans with electric motors. You can also have in between with fuel cells to produce electricity on board the aircraft with hydrogen. So you have a lot of options available to you, and it's really a pretty broad design space, and a lot of things to look at. So if I want to dig into that a little bit more and kind of look at energy carriers for aviation, it's kind of one of the first choices you're going to want to make in your propulsion selection, which is which fuel am I going to use? Certainly in commercial aviation, this decision is pretty easy in the past of I'm going to use jet fuel because that's what we've been using. It works and it's great. But there's a lot of different options here. You could use all sorts of different things. Wood is a viable energy carrier. It takes sunlight. You're taking energy from the sun, using biological processes to make something that burns. You can use that to drive some thermodynamic process, right? We can use battery, we can use hydrogen, we can use other, hydrocarbons that might be out there like LNG. Really, everything is on the table for us right now as we try to look into the future and how do we get away from fossil derived fuels. And so you start thinking about, again, with your requirements, what's going to drive what I need on the aircraft. Can I get things that have high specific energy? So as much energy as I can get for the least amount of weight. Pretty much weight is the number one driver for an airplane. So anything that's more lightweight is usually a good thing. However, I still need to make sure it doesn't take up too much volume. So I'm also looking at my, not just specific energy, but energy density. How well does it package? Certainly you can see things like hydrogen becomes very interesting because it's very lightweight, but it is very voluminous. It takes up a lot of space. It's going to hit your drag. Is that going to be a problem? And then, of course, understanding safety. Number one concern in aviation is making sure everything's safe. How can we install things with as few contingencies in place as we can? Because again, anything that we need is going to take up weight. And the more safety systems you need, the heavier it is, the more complex, the more expensive. And of course, at the end of the day, can you make it economic? Can you get your fuel at the prices you need, where you need it? So here's just kind of a quick comparison of the things we definitely look at. Jet A, of course, as the baseline. Batteries certainly is an excellent energy carrier for electricity. If we can produce green electricity, we put it in the battery. It's incredibly efficient. But you can look at these numbers and see why they become problematic. Batteries have very low specific energies. They're very heavy for the amount of energy they carry. They are reasonably dense. You can certainly package them in aircraft, all right, but at the end of the day, the weight significantly limits your range. And how you might want to deal with that. And that's why we're seeing batteries right now in aircraft mostly focused on very short range activities, things like urban air mobility that are within a city, only having to travel less than 50 miles, 100 miles. Certainly very doable on batteries. Trying to go much further, you start to look into other things. We can look at things like natural gas or e-methane type of things. We can look at hydrogen, some of the heavier hydrocarbons. There's other things on this list. You can look at things like ammonia, limonene, come up with your favorite molecule. You can make an energy carrier out of it. And so trying to go through the whole process and understanding what are all of the options and getting them in is kind of a key aspect. And anytime you're looking at any sort of vehicle configuration or aspect, this is really a big piece to understand. So what are my energy carriers going to be? How am I going to do this? There are other pieces of this. Jet A, for instance, like I said, today you basically get your fuel tank for free. You have volume in the wing. It actually makes the wing more efficient structurally to keep the weight out within the wing. And as you use it, you need less lift, and it's very synergistic with the rest of the aircraft. Batteries, not so much. You can put them out in the wing potentially, and get some of those benefits, but they don't lose weight as they fly. They are heavy. They're in the fuselage. They need a lot more structure, so your airplane gets heavier. Similar with all the other, I'll call them cryogenic or gaseous fuels. You end up having to either have cryogenic insulated tanks or high pressure tanks on board, which adds a lot of structure, adds a lot of volume, and you have to start accounting for those things. And so even though we're looking at specifically propulsion pieces, understanding how those propulsion decisions are going to affect the rest of your aircraft is key. It's kind of where we go into some stuff going forward. And the powertrain itself. And I want to go into that a little bit because it's not just about providing thrust. And I use the word powertrain specifically because an engine is all about turning energy, and what we were talking about before, our energy carriers, into power. Obviously, the number one thing is to provide thrust because we are trying to fly. Thrust is a key part of flying. You can get a glider, but even a glider had to be provided with initial thrust to get up there, whether that was a ground system or a tow. But making sure you're able to provide that thrust and that mechanical propulsive power, in a turbofan today, that's mostly internal shafting. You got an electric motors doing that, and maybe you have an engine powertrain that's providing mechanical power to an electric motor to a propeller or a fan. Maybe you're doing a direct coupling through a turbofan. All sorts of different options to get that power you need to drive the airplane. But it's not just about the thrust, and this is where a lot of the complexity of propulsion design comes in, because the power chain is really the heart of the airplane. The entire aircraft is powered from those engines. So not only do you have to provide thrust, but you also have to provide electrical power typically for the aircraft. You have to buy hydraulic power, pneumatic power. When we look at a turbofan like this on the right, you can see off to the bottom of the fan case there is the accessory drive module. And that's, again, another shaft coming off. It runs an entire accessory gearbox where you have electric generators, hydraulic pumps, pneumatic pumps coming off of the engine to drive all of the aircraft operations. You also have things like aircraft ECS bleed. So you actually pull air directly from the high pressure compressor of the engine to drive the aircraft system. So traditionally, pretty much most commercial airplanes, the air that's coming out of that vent that you open is coming directly from that compressor in the engine. It comes through, it goes through a bunch of, air conditioning, which is also driven by the engine, but to drive that air directly into the cabin. One of the few airplanes that doesn't, the 787, has since eliminated that bleed coming off of the engine and has driven that electrically through separate pumps on the aircraft, which gives some benefits. So it's important to consider, as you're doing your propulsion design, what are all of the different pieces that aircraft needs? If I'm building an autonomous vehicle, I may not need a lot of that ECS system, the environmental control system, to keep people happy, but I'm still going to have to keep avionics cooled, especially if it's autonomous. You're going to have a lot of computers on board, which also means I'm going to need a lot of electricity to drive those things. And so it's always an interaction with all of the different systems and components on the aircraft to make sure everyone, all of the different sub teams of the aircraft or disciplines are getting the power they need. It's also important, as we go through that, thinking about what is it that I need to do. And I think of my propulsion power and comparing different types of propulsion systems. So this is a kind of a high level view of, hey, if I wanted to build a new airplane, say in this case, a hydrogen airplane that could use either a turboprop, a turbofan, or a fuel cell, what are all of the things I need to think about? And this chart really kind of shows you often hear how efficient fuel cells are. They can be in the order of 60 to 70% efficient, which is fantastic because the turbofan is only about 35 to 45% efficient, and turbo shafts are usually much less efficient. But what you don't always think about are what are all of the other pieces that I need to do. So if I need propulsion power, and I'm looking at these three things, and I have a 60% efficient fuel cell. Well, to get that fuel cell to operate, I need air handling. So it needs basically a turbocharger on board to make sure that it's getting air at the pressure it needs as you're in altitude. You need an electric powertrain to drive a propeller, and the propeller itself has efficiency. So when you start stacking things up, there's always a range of things and a balance of things, and you can see. Today, turboprops might be less efficient. Turbofans are quite efficient, at least at the larger scale. Fuel cells are also quite efficient, but they have a lot of things to break them down. So you can get a lot of efficiency out of a fuel cell, and then you look at the next thing, which is the weight, and you're like, well, turbofans have certainly optimized for weight. They can be 5 to 10 kilowatts per kilogram. They're incredibly lightweight and efficient. Turboprops, again, they've been designed in their history to be, again, thinking of the requirements, super reliable. A lot of the turboprops are really built like, I call them like tanks. They're very flexible in their operational range. They've given up efficiency for lightweight, but also ease of maintenance and ease of use. And then when you start looking at fuel cells and all of those things I said before, like the fuel cell themselves, the air handling, the electric powertrain, it gets very heavy very quickly. So yeah, maybe you can get up to 2 times more efficient than a turboprop, but you're going to be 4 times heavier. And so that gets into a lot of different trades that you have to do as an engineer to understand what do I want? And it's going to depend a lot back on that mission that we talked about at the beginning in the requirements. If I have a shorter range mission, maybe I can get away with more weight, or if I need a really long range mission, that weight that you have to carry that whole time can really start to hurt. But if my fuel's lightweight, maybe it pays off. So there's a lot of trades you need to do. Now I talk about propulsive power, but if I wanted electric power, the story will start to change on us. Now, say I'm looking at something like a power generation unit. Um, Typically, we use a gas turbine APU. Again, it's basically just the turbo shaft from before, but now instead of a propeller, it has a generator on board. Those tend to be very inefficient relative to everything else, but um, it's because they're small, packaged, and when you're running them on small scale, it's still better than trying to run the main engine and get generation. Obviously, what we do today during flight, operating a turbofan core offtake, are very efficient. You have the 35 to 45% efficiency with a high efficiency generator. But if I have a fuel cell available to me, now I get to take account for that 60% efficiency. So if I want electric power, fuel cell by far can be one of the best options out there. And again, it can start to win even on weight as well. It's still a little bit heavier. Fuel cells are big chunks of metal, but their efficiencies can really start to pay off. So you start doing all of these trades, trying to understand how I'm going to use something, where I'm going to use it, and what I'm going to do. And it kind of gets us down to some of our our sensitivity analysis, and trying to understand, pulling all of those things together and understanding, how do these things compare? And so one of the ways that I've come to like to compare some things is look at what is the overall efficiency of the system and how things are going to work. And really, I can do a for any given design range mission, kind of using the same energy carrier and the same airplane, you can create these basically lines of constant efficiency for the vehicle. And so I can use on a chart like this, I'm trading propulsion efficiency on the left side of the chart with propulsion system weight, and I can start understanding how things work. And this specific chart was brought up, started putting this together to understand, with tomorrow's new airplanes, we're looking at replacing turboprops with fuel cell airplanes, and how whether it's better to invest in fuel cells, in electric powertrains on an aircraft versus updating turboprop technology. So today, any turboprop flying around is basically built on 1980s and previous design. There hasn't been, brand new turboprop systems architecture like there has been for turbofans. So if we were to just modernize technology, for instance, how much more efficient could we do just based on all of the things we've learned about turbo machinery over the last few years? And then once you take that and want to go into the future, can I start trading weight for efficiency? I can do things like recuperation or, adding more cooling technologies and different things that today turboprops have been optimized to be lightweight based on today's missions, but tomorrow's missions are going to be different. They have different goals and requirements, particularly with emissions. So what could I do to today's design to do that? At the same time, we can take, hey, what are today's, optimistic fuel cells, and also apply lots of technology to those to get, how do we progress and invest in the technology? And what's actually fairly interesting is there's really a tight race between the two. As we start looking at what a 2040s, 2050s aircraft can look like, there are certainly a lot of options in the way you can do things. So, particularly turboprops, one of the interesting things, they are short-range aircraft. So we can start, you have a little bit of options to play with there, where efficiency, you can tell by the shape of these curves is much less sensitive. Weight is much more sensitive than weight. So getting that more efficiency certainly is a key. You could also throw other things on this chart. I think if you were to put, for instance, a piston engine. So if you wanted to go to, what GE uses for pistons, they tend to be actually a bit more efficient than turboprops. But they are much heavier. So they're probably somewhere in the middle between these two. which are another things they could work in, although they can get very heavy at these scales, but work for smaller sizes. So this is kind of taking into how we can operate these different things. You know, you can pick which solution is the best, but at the end of the day, one of the key thing, and probably the hardest things to work on, is safety and certification. And I wanna bring this up a lot and introduce you to a lot of the things that that we're always thinking about in terms of commercial aviation, particularly where you're gonna have to certify, be safe, and get people out there. And this is where I see a lot of designs start to fall short and fail because you haven't fully considered what you need to do to put an aircraft in service. What you often see, and you know, we're all guilty of this, is, you know, looking at new technologies and you start thinking, oh, this is fantastic. I can get much more lightweight than current existing things. I can get better. You know, you hear a lot actually with electric motors. Oh, they're going to be much more efficient, much more maintainable. But the problem is they're new, they haven't been tested, and you don't know all of the additional weight that you're going to have to go put in because of all of the safety things that you're going to learn during testing and development. So really, I put a couple of things on here. I'll talk on a few key things of these, but there's this kind of growing list of expectations for Part 25. And for those of you who haven't looked or heard of FAR or Part 25 or Part 33, the FAR, the Federal Air Regulations, which is 14 CFR, which is Chapter 14 of the Code of Federal Regulations, which is basically everything the FAA puts out for what you need to do to certify. I highly suggest just type into Google 14 CFR. It'll pop up. You can go look through all of the different options. 25 is probably one of the key chapters, which is, you know, certification of a large commercial airplane. Part 23 is a smaller airplane. 33 is engines. There's a whole bunch of things out there, but things to go look at. And, you know, they cover things, you know, chapters here that we put out and the specific rules around, you know, lightning strike. For instance, you know, when you start thinking about jet fuel today, you know, we have all sorts of, you know, systems running through the aircraft to redirect a lightning strike to avoid the fuel tanks, to make sure you don't have an ignition source. If you start changing your fuel, you're going to have to think about what that does. What's a lightning strike going to do to a battery? What's it going to do to your electrical system? What sort of systems do you need in place to get things around that? Bird strike tends to be another one. You know, if we start looking at today's fuel tanks are protected by the leading edges of the wing. If we start putting external fuel tanks, or, you know, looking at a lot of the hydrogen options, you start seeing larger and larger fuel tanks take more cross-sectional area. What happens if now they're exposed to bird strikes? System separation or rotor burst, you know, that's kind of the picture we have there. You know, anytime you have parts that spin, there's a chance that they, you know, gas turbines spin very quickly and have a lot of energy. And so there's different requirements depending on the energy of the system, where those rotor discs might go, what parts of the aircraft they can impact, and making sure that if it does happen, that you keep both people safe and keep the aircraft safe, and for continued safe flight and landing. So there's all sorts of things like that, making sure, you know, you don't have a constant with the system separation. You don't want one blade to go through and cut all of your hydraulic lines at one time, and all of a sudden the whole airplane loses hydraulics. We've certainly learned that lesson from the past, and now new airplanes don't have that. But a lot of times, especially in early conceptual design and understanding of how you're going to put a configuration together, certain configurations might look really good on paper, and really good from, you know, a performance and standpoint, but when you start assessing them against, you know, certification and safety criteria, they start to break down because you can't handle things like a rotor burst, or if a propeller lets go and it hits the other propellers. types of things to think about. So how you position things, how they line up, and we get into things like crash fault, piping, what happens to the engines in a crash. So all sorts of things to think about. Definitely, it's a slog, but I highly recommend just getting out and at least looking at all the chapter titles under part 25 and part 33, if not trying to go through a lot of the details and getting an understanding of what it will actually take to get an aircraft fielded. It's easy to get an aircraft into an X-plane scenario because it's very monitored and controlled. You don't have to follow much of the rules because you're going to be flying within a very controlled airspace. But to get certified to be able to fly anywhere, anytime, commercially, or even non-commercially, is a very difficult, time-consuming, and involved process, and it's actually where most of the expense is in creating a new aircraft. And of course, propulsion is at the heart of most of these. So if I bring it down, I'll give you some of our conclusions of, I've been talking about energy carriers a lot. Where can we get different airplanes? How does this all come together? Certainly, I'd love for everyone to ask questions and stuff, but you start looking at where can I use different propulsion systems, different energy carriers. Again, where can these things fly? So the things that we're looking at now within Boeing, we're certainly exploring the entire space and stuff beyond this and figuring out how we can make these things happen. Certainly sustainable aviation fuels, those are our kerosene drop-in replacements. Certainly our number one focus. Those will work because they drop in, they work in today's systems. We're worried more about getting enough of it in the future. So we're looking at what are all alternatives. Battery electric certainly works great in the low space. We're working through a lot of the challenges of electric powertrain systems. We have work going on with things like WISC and EPFD to understand how those play in the commercial airspace. Going into the hybrid electric, you can get a little bit more range, a little bit more applicability out of those electric powertrains with only using a little bit of things like SAF, so you can kind of make your SAF last longer through those options. We start looking into fuel cell electrics. Obviously, those are similar to the hybrid. You're limited by the weight of the electric powertrains and how heavy they can get. And then hydrogen combustion at the larger scale certainly starts working out, but we're looking at a lot of airport and infrastructure challenges. How do you get enough fuel where you need it and enough energy? So kind of to bring it back at the beginning, looking at what are your requirements, different sizes of airplanes, different missions have different requirements. You may select your energy and propulsion system differently based on what that is. If I need a 500-mile range, so turboprop type vehicle to just move people around, maybe island hopping, and it's within a small region that has hydrogen available because they have lots of green electric energy and water available. A fuel cell electric airplane is fantastic. Or maybe I'm regional hopping around the U.S. with this kind of a same mission where a hybrid electric might be better. I have lots of SAF available, or I'm doing urban air mobility with battery electric, but now I need to figure out my long haul. Maybe I can modify just a couple airports for hydrogen and keep those going. So always thinking about this broader scope. Again, understanding what are my requirements, how am I going to interact with the rest of the systems on the airplane, and keeping track of all that and managing the sensitivities. How does trading weight and efficiency going to play out? What is my systems going to look like? Am I keeping everything safe? And I'll use that to end here. I suggest, by the way, if people who are interested in sustainability, got to do our sales pitch for our Cascade tool, which kind of shows how we're thinking about alternative fuels and how they work within today's current fleet networks, and how to balance, again, the requirements of different energy, hydrogen versus SAF, and how we might implement them across the current aircraft fleet and what the impact might be, so we can come and create strategies to get us to net zero by 2050. So with that, I want to say thank you guys all very much for listening to me, and happy to answer any questions.
Dom, thank you so much. An incredibly informative presentation that I know our teams will find incredibly valuable and will probably need to review a couple of times also. So let's start with a question that we have with regards to the hybrid electric power plant systems, i.e. Aurora's turbine-based lightning strike. Are gas turbines or piston ice engine systems more fuel efficient and reliable?
So that's a great question. So if you're looking at, a distributed hybrid electric propulsion system, so you have a lot of, maybe say, small fans, lightning strike, I think, had, I forget the exact number, something around 20 or so fans driven by a single gas turbine. Again, it comes, actually, it's directly, let me see if I can get my, go back in my slides here real quick. We're starting to think about kind of in this sort of trade space. You've got, or even, back here, you're basically trading your weight and reliability and cost. What you have is your turbofans tend to be very lightweight and extremely reliable. So you get a lot of life, you get a lot of good efficiency, especially if you're staying on condition. So a gas turbine is really good at max power, and if you're staying at max power, or at least at a consistent power, your turbofan is going to be very efficient, and very lightweight, and very reliable in terms of maintenance timeframes and long endurance there. If you're comparing that to, say, an internal combustion engine, a nice piston engine, piston engines tend to be much heavier, right? You've got a solid block of metal that is your engine block, with pistons that are heavy, that have to move back and forth. They get very heavy very quickly. The benefits of a internal combustion engine, though, is they are much more efficient over the range of operations. So they'll be nearly as efficient at low power as they are at high power. They're much flatter efficiency curve, and they will be slightly more efficient. So what it comes down to is, if you're looking at your specific aircraft and its mission requirements, can you handle the weight of that engine for its benefits and efficiency? Now, when you're looking at something like distributed electric, you're going to be operating in something like lightning strike nearly high power most of the time. So that's why you might end up with a turbo shaft driving generators to everything else in there. And also for the weight, anything that takes off vertically particularly is going to need a lot of weight, or lightweight systems to do that. So that's how you would sort of think of that problem. And again, just understanding how you play your sensitivities against each other, it would certainly be a trade worth exploring.
Can you share your thoughts on using a steam-powered system? It can burn Jet A or diesel and is very low noise and generates massive amount of torque, and it allows for more complete combustion of fuel.
Yeah, so using a Rankine cycle as opposed to the Brayton cycle, where Rankine is the steam cycle, Brayton is the gas turbine cycle, or the Otto cycle in an internal combustion engine. Couple things to think about. First of all, the combustion efficiency itself in a gas turbine is nearly 100%. You're really not going to get much more benefit from going to the steam cycle and being able to have combustors. Certainly, you even look at today's ground power systems. A lot of the, I would call it, for power generation on the ground, small systems, they actually use aviation gas turbines. Because they're more efficient, they're easier to set up. You only get into the steam cycles when you're doing large coal plants or nuclear power plants to drive the steam cycles. And certainly, they're all based on turbines, so it's really, at the end of the day, very similar technologies. So unless you have a specific reason to go to a Rankine cycle, more than likely you wouldn't do it in these cases. And really it just comes down to weight. It's going to be very heavy. You have to have your working fluid. If it's steam, you have a bunch of water on board. You've got a bunch of extra systems. You're going to add a lot of weight. You may be able to get a little bit more efficiency. I'm not sure, haven't really thought about that one too much, but I do know you will add a lot of weight and a lot of actually complexity, as opposed to going to something like a gas turbine, which has most of the same components already and does it very well.
How long roughly does it take a new battery technology to get certified? If a new battery is working with the lab, how many years away would it typically take to find its way into an aircraft?
Yeah, that's a long time is probably the short answer. We're still, when we look at batteries today, there are a lot of very interesting battery technologies that keep coming up around the cells. I could probably give an entire lecture on just battery technology integration, but when you start looking at a battery, the first key is to understand what level you're already looking at. Are you looking at the chemistry technologies, which they're working on creating a cell? So that cell, that's like your, wish I had a battery sitting here, like your AA, AAA battery, that's a single cell. You're basically taking a whole bunch of those, putting them together to make a pack. You put packs together to make a module, and then you install that module into the airplane. What really is going to come down to for aircraft certification is understanding actually the safety of all of that. Can you make those cells reliable, and as you're designing the cells, making sure that they have wide temperature ranges that they can operate under, that they can operate under the loads for a long time, that they don't degrade too quickly, and then making sure that you can do that safely. One of the things that happens with batteries is you have thermal runaway. So you have this huge pack of batteries. They have a couple thousand cells in it. It only takes one cell to start going off. If it goes into thermal runaway, it will all of a sudden start taking out all of the batteries around it. And that's actually, even with lithium ion today, it's the number one challenge. That's a known chemistry today. So being able to safely manage and control the battery system as a whole is key to that. And I think the FAA, EASA, there's lots of I think the SA 40 committee, professional organizations spending a lot of time with a lot of people from the entire industry trying to work through how to solve these problems. But of course, you have all of the companies doing their work. Wisk is working on their battery systems, and our competitors and Archer and Joby are working heavily on that. We're working with other folks as well, like GE with EPFD. But it's certainly it's a number one problem to understanding how to integrate high power dense batteries that we could possibly use for propulsion. So the short answer is I don't know, and I think it's going to take a long time, and it takes a lot of work to make sure it's safe to get a battery on board an aircraft.
There's a question for our team. What is the best way to certify for airworthiness? How should we approach this? So we have been working with the FAA for a couple of years now. So we did a lecture with them in August. We would encourage you to review the FAA lecture. We also have a team of FAA advisors who will be supporting all of the GoAERO teams to certify for airworthiness and what they need to do to participate in the fly-off. So we will certainly be in touch with more details and checklists on how to approach that process. So we encourage you to make sure that you're registered on the platform if you're not already, at herox.com/GoAERO, and continue to look for those resources. And we will certainly make sure that you have what you need in order to approach this process. Dom, another question is, do engines and motors need to be certified for ultralight craft?
Well, let's see, I'm not super familiar with the ultralight certification rules. So then you get into the question of what is a certified aircraft. So the short answer is if it's a certified aircraft, yes. Certified aircraft typically fall under 25, 23, and both of those require Part 33 engine certification. And then I think you have Part 35, which is propeller. So if you have a propeller aircraft, I know there's one for balloons in there as well, and there's another one for helicopters. I'm not as familiar with those. I could probably go pull up the list and go through it if you wanted. But in short, if you have a certified aircraft, yes, you need to have a certified propulsion system. Now, there are, a lot of home-built aircraft, which typically a lot of ultralights can fall under this, or basically you can fly without being certified. So there's a bunch of rules there. Again, I am not the expert to talk about that, but if you want a certified aircraft, typically anything you're going to use for commercial use, anything you're going to make money from, you almost always need to have a certified vehicle. So in that case, yes. If you're just going to do an X-plane or some sort of experimental vehicle, then you don't necessarily, you have different rules of certification. You do that one on. I assume your FAA lecture would cover a lot of this, so hopefully that I would again go back and reference that, or work with the FAA rules on that.
Yes, absolutely.
Yeah.
Is there a FAR for dummies that you can recommend? In particular, they're thinking, is there a website?
That's a really good question. There isn't one that I know of. Because really at the end of the day, you'll go through the whole FAR for what you want to do. I will say, myself as an engineer, I've read through all of the propulsion and most of the aircraft ones. There's advisory circulars. That's another thing I mentioned. I had some of the numbers up there. That will talk about, like, if you see AC 20.128, which is an FAA interpretation of the rules, right? For rotor burst, it'll tell you what it means and some more of the details. But at the end of the day, I wouldn't say that there's a good, simple overview. It really just comes down to knowing and understanding all the different pieces. You kind of have, it's kind of an all or nothing thing, unfortunately. But there probably would be some good summaries out there. And if anybody finds some, let me know. I should probably go look at that. It's been a while since I've learned about this stuff. But certainly asking experts is probably the best way. Ask people who know. If you ever want to become a pilot, one of the first things you do is you get a flight instructor, and that's basically your introduction for dummies. They get you up to speed. So using mentors, using experienced people is really the key to all of this.
And we'll take one last question now. Can you discuss a little bit more thermal management, especially as internal combustion air breathing rejects much of it, 65% inefficiency in the exhaust?
Yes, that is one of my favorite things to say about a jet engine as opposed to an electric machine. The jet engine might be 40% efficient, but that 60% efficiency goes out the back as heat in a hot airstream, whereas an electric motor or a fuel cell might be 95% efficient, but all the heat is stayed inside. So actually, one of the key aspects to a lot of these different system designs, again, one of the things that drives up weight quite a bit is how do I deal with that heat? And not only do my electric machines, produce, it's smaller amounts, but it's internal. It's also low quality heat. And what I mean by that is you have a low temperature differential. So for instance, a fuel cell might, it'll want to operate only maybe up to 100 C. A lot of the, PEM, proton exchange membrane, fuel cells, are based on moisture content at about 1 atmosphere. So if you get above 100 C, you start to evaporate too quickly. Now, if I need to operate less than that, maybe my fuel cell wants to operate at something like 60 C, and hey, I have a hot day takeoff, and I have a requirement to be able to take off at 40 C. I only have a very, very small delta temperature to deal with, and you can end up with very large heat exchange systems to do that. You can certainly think in, in your internal combustion engine car, it's really obvious. You have a bunch of liquid cooling that goes, your radiator fluid goes, in through the engine, picks up heat, goes through the radiator to your fans to blow over. It's all kind of the same thing. Jet engines, particularly, they also have, internal cooling systems. You'll use your fuel to cool things. You have oil loops going around, but typically the only heat you have to reject from the engine are things like the bearings or some conduction losses into the thermal system. But typically the air itself flowing through the engine is taking away most of the heat. So yes, focusing on how you're going to keep everything cool, and don't forget about the hot day you're going to have to take out often. So, we talk about high hot a lot. Think about taking off and a place like Bogota. You're at 10,000 feet and it gets hot because you're near the equator. Can be very difficult and challenging for aircraft. And so understanding if your aircraft needs to operate there, or if it's, on the flip side, are you going to be operating out of Anchorage on -40°C days, where it's very cold, and being able to operate at both of those can be a real challenge in thermal management. So make sure you're always, you can focus in on that nominal standard day, a nice 15°C, 59° Fahrenheit day, but that's the easy spot. You always think about, how to operate hot and harsh environments. Can be very difficult, particularly in thermal management systems.
All right, Dom, thank you so much for all of this information. We really, really appreciate it. As a reminder to everyone on the webinar today, the recording will be available on our website in the next few days, and we will also be sending it out via email so that you have access to it and can review it as you like. As a reminder, if you are not already registered for the competition, please be sure to do so at herox.com/GoAERO. It is a very straightforward process, and this way you can continue to get information about the resources that we have available for you. The stage 1 submission deadline is December 11th, so please continue to work on that and reach out to us if you have any questions. We also have another expert lecture coming up next week on the 24th, so please stay tuned for that. Dom, thank you once again so much.
Yep. It was a pleasure, and feel free to reach out with any questions. Thank you.
Take care. Bye-bye.